Welcome back. We are in the new lecture in power electronics. We are going to discuss on power BJT, characteristic, structure and applications. The outline goes like this. First, we will discuss the introduction, the operating principle of BJT, the static characteristic, what are the safe operating area, the dynamic characteristic, base drive circuit, thermal management, some of the application and design examples. We'll compare it with other power devices and conclude our discussion. So at the end of the lecture, you will be able to understand the structure and operation of power BJTs. You will be able to analyze the static and dynamic characteristic, design appropriate base drive circuit, apply thermal management principle, and compare the power BJTs with other switching devices such as MOSFET and IGBT. Select power BJTs or specific applications. So the power BJT is basically the bipolar junction transistor optimized for high power switching and amplification. So basically two important application of BJTs are the switching and second is amplification. So the BJTs are basically used in high power, so it is known as power BJT. The voltage rating is in the range of 50 volt to 1500 volt. Current may go up to 500 ampere plus and power may be several kilowatt. The basic key difference from small signal BJTs are it is larger die size, enhanced thermal packaging and optimized for switching applications. The symbol for NPN and PNP type transistor, which is similar to what we have discussed in the original transistor and the power transistor, it will be same. So two important categories of the BJTs will be in the form of NPN or PNP mode. The structure of power BJTs, so the key structural features, you will be having the emitter, the base and the collector. Emitter is basically heavily doped with the N-type or P-type material. Base is lightly doped and thin. Collector is thick, which is slightly doped for high voltage. And there is a epitaxial layer for high voltage blocking. The substrate is heavily doped for low resistance. So here you can see the basic epitaxial planar structure of a BJT, and the emitter, base, collector are shown, which is in the NPN mode. There is a substrate which is heavily doped for low resistance. If you can see, the thickness of this BJT is in and around 100 to 500 micrometer. So some of the important package types are TO3, TO2108, TO247. These are industrial packages which are moduled and press back assemblies are present. The operation mode of power BJTs are in three mode. One is the cutoff mode, the second one is the active mode, and the third one is in the saturation mode. In the cutoff mode, the base to emitter voltage threshold level will be in and around 0.7 volt. It has to be in operation. There will be no current in the base, and the collector current will be the reverse current, which is the leakage current, collector to base leakage current. The transistor will be acting as an open switch. So when you have in the cutoff mode, it is in the open switch operation. In the active mode, the base to emitter has to cross this threshold level of 0.7 volt. The collector to emitter will be greater than the collector to emitter saturation level. Then only the transistor will operate properly. The collector current will be beta times the base current, and it will have a linear amplification region. So the open switch has now become in the amplification, which is in the linear region. In the saturation mode, there will be high base current and the collector to emitter voltage will be less than its saturation limit. Collector current will be less than the beta times base current because the current will be limited by the load resistance. Transistor will act as a closed switch. So these are the three important modes of power BJTs which are shown in the characteristic, where you have the collector current versus collector to emitter voltage. You have the saturation mode here in the active region, which is a linear amplification region, and then you have the cutoff mode. The current relationship and parameters, the basic relationship that we use in BJTs are you have the emitter current is equal to base current plus collector current. The collector current is equal to beta times base current, and then small amount of reverse saturation current will be there. Alpha is the current gain, which is collector current by emitter current. Now collector current you can write as beta times base current, and emitter current you can write as beta plus 1 time base current. So base current will cancel out each other, and you will have the alpha parameter in terms of beta, which is beta by beta plus 1. The same, if you want to find the beta in terms of alpha, it will be beta equal to alpha by 1 minus alpha. So these are the basic relationship, the most important equations which are required to solve any type of numerical problem in the BJTs. The typical power BJT parameter with a beta lying between 10 to 100, it is lower than the small signal mode. The base to emitter in the on state, you will be having 0.7 volt to 1.5 volt, and the collector to emitter saturation voltage will be 0.2 volt to 2 volt. The collected to base reverse saturation current has to be less than 1 milliampere at a temperature of 25 degrees centigrade. So if you see the circuit connection to find the current and voltage in a BJT, so this is the BJT, and you are having a voltage which is connected as collector voltage VCC, and there is a voltage which is connected at base, so this is VBB, and the resistor will limit the current. So resistor of the collector and resistor of the base are there. The three current will be the base current, the emitter current, and the collector current. So these three current will be forming the equations, and we can relate it with respect to the KCL equation. Input characteristic here is the characteristic which is drawn between the base to emitter voltage and the base current. So base to emitter voltage is on the x-axis and the base current is on the y-axis. So that will give you the input characteristic of BJT. It is in the form of exponential, just like the diode. And the important relationship, we know that base current is equal to the saturation current Is, and it is exponential relationship with respect to base to emitter voltage and the voltage Vt, which is the threshold voltage. So temperature dependent this current is there, because once the temperature changes, because Vt parameter will be depending on the temperature. So if the temperature changes, the Vt changes, and as a result the base current will also change. The base to emitter will decrease in an approximately 2 millivolt per degree centigrade. So these are different for various collected to emitter values. Here you can see the characteristic. So there is a threshold limit here which is 0.7, after which the BJT will start conducting. So here you have the different waveforms for different values of the collector to emitter voltage. So collector to emitter voltage has to be fixed, and then you will be getting the base current for a particular base to emitter voltage. The practical implications of this design is basically the base drive design is critical here, and the temperature compensation will be needed, and current limiting resistor is always required for the input characteristic. So these practical implications or practical need has to be there in order to properly operate the network. The output characteristic is basically the relationship between the collector current and collector to emitter voltage. So here you have on the x-axis collector to emitter voltage, on the y-axis you have the collector current, and the region of analysis are divided into three important regions. One is the saturation region, second is the active region, and third is the breakdown region. In the saturation region, you will be having the collector to emitter voltage less than 1 volt. So here you can see it is just starting, and less than 1 volt you are having the saturation region. In this region, the output characteristic curve has a steep rise in the collector current. The collector to emitter saturation voltage is low here, which is desirable, and it is used for the switching application. So if you require to use the BJT in the switching application, you go for the saturation region. In the active region, which is collector to emitter voltage greater than 1 volt, so you are crossing here the 1 volt, then you will be getting a constant collector current for a given base current. So you can see that these are the given base current and the collector current is constant. The curve is shown from 10 microampere to 80 microampere. The collector current is equal to beta times the base current. So you are getting a linear characteristic, and it has a slight positive slope due to the early effect. So if you see this is although linear, you have certain slope here due to the early effect. So breakdown voltage or breakdown region, what we say here, which you will be getting only when the collector to emitter voltage will exceed the basically the breakdown value, which here in this case it is shown as 40 volt. And this will lead to avalanche multiplication, which is the avalanche breakdown, and there will be destruction if the current is not limited up to a certain limit. The transfer characteristic and the key parameters. So DC current gain is generally given by beta or it is HFE. So beta, which is the DC current gain, is the ratio of the collector current by base current, and it is in the active region. It varies with the collector current. So once the collector current changes, also dependent on collector to emitter as well as the temperature. So typically, the value of this beta ranges from 20 to 100 for the power BJTs, and these are designed for worst case for the minimum beta. So this is the DC current gain parameters. If you can see here, this is the collector current and you have the beta here, which is the current gain. So if you see that once the collector current increases, the beta will also increase up to certain design point, after which it will fall. So you need to operate for the current if under the below the optimal value. The saturation parameter, you will be having, saturation means the maximum, so collector to emitter saturation you will be having as the collector to emitter saturation voltage. The base to emitter saturation will be there, which is base to emitter saturation voltage, and the overdrive factor, which is given by the ratio of the base current IB, which is in operation, by base current, the minimum value that is required for the BJT operation. Typically, this collector to emitter saturation voltage lies between 0.2 volt to 2 volt. So here you can see the curve between the collector current and collector to emitter saturation voltage for different ODF value over drive factor for 2, 5 and 10. So you will be having the minimum current which is required for the base for the operation. The safe operating area is basically that region of characteristic between the VCE, that is collector to emitter, versus the collector current, where the device will operate safely. This is generally bounded by multiple failure mechanisms. So it is critical for the reliability and device protection. So this is the safe operating area of BJT, which is the curve drawn between the collector current and the collector to emitter voltage. And you can see here, when you need to operate the transistor for in the safe operating region, then we should know the safe operating area where you need to operate. What is the maximum current and what is the maximum voltage that we have to pass through the BJT. So these limiting factors, when we say it is limiting, so the limiting factors depends upon the maximum current, which is dependent upon the bond wire or metallizing limits, power dissipation, which is limited by the thermal, breakdown voltage, the highest collector to emitter breakdown voltage, the secondary breakdown due to the current crowding will be there. So safe operating area is what we need from the datasheet, so that we know that where the BJT has to be operated so that it doesn't fail. There is second breakdown phenomena, which is basically the mechanism where there is a current crowding due to the negative temperature coefficient. So due to the negative temperature coefficient, the current will be crowded, which is shown here. Due to the current crowding, there will be hotspot formation, and these hotspot formation will result in the local current increase. So hotspot generally form when there is a local current increase. The positive feedback will result in the thermal runaway, and this occurs at a very high collector to emitter voltage. So if you keep on increasing the collector to emitter supply, then the collector to emitter voltage will increase and there will be thermal hotspot formation, and that will result in the breakdown. So there will be moderate collector current. So some of the prevention methods are given where you can avoid this secondary breakdown phenomena. Like for example, you can have interdigited emitter region. There is a ballistic resistors which you can use. Current sharing circuit, when there are too many BJTs in the circuit, you can share the current. Proper thermal management has to be done, and you have to operate the BJT within the safe limit of the operating area. So here you can see the current density and temperature. So if the temperature increase again due to the current density, there will be hotspot formation, but you have to operate the BJT under the normal region. So current crowding, you have to avoid it. Now, the switching behavior of this BJT, we will see the key challenges. So, there is a minority carrier storage in the base, due to which there is a charge removal during the turn off process, which is required. So, even the transistor is turned off, some amount of charge will be there, and that has to be removed. This is very slow switching compared to the MOSFET. So, if you compare the BJT with MOSFET, it will be having the slow switching. So, this turn off time should be very, very greater than the turn on time. So here you have the switching waveform of the BJT. So with respect to time, you can get the amplitude, but is the switching phenomena for different values of the base current, and what is the delay time, rise time, the saturation time, and the fall time. So you can see the curve here. So this is what you have, the delay time, then you have the rise from here, and then you have the settling time, and then you have the fall time. So collector to emitter voltage is shown, the base current is shown in this switching waveform. Generally, this range of switching times, if you see, the delay time is in the range of 10 nanosecond to 50 nanosecond. The rise time is in the range of 50 nanosecond to 200 nanosecond. TS, which is the storage time where the charge is stored, it is in the range of 100 nanosecond to 500 nanosecond. And when the charge falls, there is the fall time where completely it has to be switched off. That is in the range of 50 nanosecond to 200 nanosecond. The turn-on process analysis, if you do for the phase 1, that is the delay time. So the base emitter junction, it is charging, and the base emitter will rise from the 0 value to base emitter threshold limit. So threshold is the maximum or the minimum where the diode will start, BJT will start conducting. So there will be no collector current flows. So the delay time is approximately equal, which is given by certain time and the factor of the base voltage. So TB, which is the constant, time constant, and this TB time constant is given by the network values of the resistor and the capacitor. So RC network formation is there. So multiplication of resistor and capacitor, you will get the time constant, and it all depends upon the base voltage and the base emitter threshold voltage. Phase 2, you have the rise time where the collector current will rise exponentially, the collector to emitter will begin to fall, and the active region operation will start. So here you will be having the rise time expression where you have the expression depending upon the time constant TB, and there is factor which is depending upon the collector current. So collector current final by 0.1 times the collector current final. So this is the equivalent circuit during the turn on of the BJT. So BJT is basically represented with the network having a diode and a current source. You know that BJTs are basically current control device. So it is represented by the dependent current source, which is beta times the base current, and all the sources are being connected, and the load register and the base register for limiting the current is connected. So the turn on time for which the equivalent circuit is shown, and we need to find the delay time and the rise time for phase 1 and phase 2. Turn off process, where the phase 1 you have the storage time, which is basically the excess base charge removal. So whatever the charge is stored in the base, you need to remove it. The collector current will remain constant here. Collector to emitter will remain at the saturation value, and this is dominated by the minority carrier. So minority carriers are the one which is resulting in the charge flow, and this has to be completely removed. So the total storage time is equal to, dependent upon a factor which is TS, this is again the constant, and this is equal to ln of the base current on state, base current off state summation divided by base current off. So phase 2 you have the fall time TF, where the collector current will decrease exponentially, and the collector to emitter voltage will rise to its collector voltage supply. Transistor will enter in the cutoff zone, and the fall time is generally given by the base current, base time constant ln of 9, which is 90 to 10%. You are basically bringing down the voltage. So storage time constant TS, which is used in here, is basically calculated using the factor tau n, which is basically the minority carrier lifetime divided by the overdrive factor of a particular BJT operation. So this is the charge control mode, where you have the base charge distribution of a BJT from its emitter junction and the base collector junction. Depend upon the total thickness of the base, you will be having the charge density, which is again the exponential in nature. So what is the normal operation, what is the saturation mode, and what is the excess charge which is present and need to be removed is shown in this figure. Switching losses you need to calculate, which is the turn on losses. So turn on losses, it is basically E on, which is integration from 0 to T on time and multiplication of collector to emitter voltage and collector current with respect to the time dt. And if you integrate it in the time on time, then you will be getting approximately equal to 1/6 VCC into IC and the total time of delay time plus rise time. Turn off losses, if you calculate, then it is E off, which is from 0 to T off, the collector to emitter and the collector current product integrating with respect to time. So you will get 1/6 VCC into IC and the summation of TS plus TF. If you see these two expressions, these are more or less same. Only difference is there in the time expression. So here you have delay time plus rise time. Here you have the storage time plus fall time. Then you will be having the total switching power, which is power is again the product of E on plus EF. This is summation multiplied with Fs, which is the total switching frequency. So typical values, if you see here, the turn on time is around 100 nanosecond to 300 nanosecond. The turn off time is 1 microsecond to 5 microsecond, and the storage time will be dominating the turn off. So how much storage is there in the device, that will be dominating what will be the turn off time. So if you see the switching loss diagram, so with respect to time, this is the E on or turn on power loss, and this is the turn off power loss, and then you have the conduction. So if you can see here the power, which is in kilowatt, as the total power of switching on and switching off. This is the instantaneous switching power losses. The base drive requirement is there because you need to have the turn on requirement, which is sufficient when the base current in the on state is greater than the collector current by the beta times, which is the minimum value, and the overdrive factor for the fast turn on, you have the beta on is equal to ODF into beta minimum, and typically this ODF factor lies between 2 to 10. So you will be having low impedance drive source, but the turn off requirement, you will be having the negative base current for fast turn off. The beta off current will be equal to negative sign here, beta on by 2, which is the typical value. The low impedance path will be there for charge removal, and a reverse base emitter is required if needed in the certain cases. So this is the base resistive drive network, where you have the transistor here and the sources are connected. So all the important design equations of the base current, the register of the base, what is the power loss, collector current and collector to emitter voltage as per the KVL and the KCL equations are shown here. So there are advanced base drive circuits in the form of push-pull drive or Baker clamp network. These are advanced circuits. These circuits have certain features as well as advantages. So they are used when you require fast turn on and turn off, you require low output impedance, you can have the positive and negative drive capability. Some of the advantages of these advanced circuit, it will prevent the deep saturation, it will reduce the storage time, the base to collector voltage will clamp to diode drop, and you will have faster turn off. So apart from the normal base drive circuit, you can have advanced base drive circuit in the form of push-pull drive network or Baker clamp circuit. So Baker clamp circuit, if you see it, there are one diode and one transistor which is used in the network. So that is basically the Baker clamp circuit in general. And in the push-pull drive, you will be having two transistors connected in the mode of PNP and NPN together, connected together. That would be push-pull drive. So this proportional base drive concept is where the base current is proportional to the collector current, and there is automatic adjustment there for the load variation. You will have constant overdrive factor, and this will improve the efficiency. So here you have the current transformer drive network, which is shown here. So this is your transformer in the ratio of n:1, and this is connected with the diode and BJT. So this is your BJT which is connected. So this implementation will be having when you have current transformer coupling, you have the current mirror circuits, feedback control systems are connected, turn ratio will determine the drive level. So some of the advantages here you will be having, as it is self-regulating, it reduces the drive power, there is isolation between the control and the power circuit. Next, we will do the thermal characteristic and management. So the power dissipation, which is the summation of power conduction plus power switching. Power conduction is given by the product of collector to emitter saturation voltage multiplied with the collector current multiplied with the duty cycle D. The switching power is again the losses due in the on state plus off state multiplied with the switching frequency. So this is the thermal equivalent circuit which is shown here, and you have this current source which is shown as PD, and there are different part of the circuit which is shown by different element like the junction, case, sink and the ambient, where you have been represented with the resistors and the capacitor. So this thermal resistance network, where the Tj is the temperature of the junction, which is equal to Ta, that is the temperature of the ambient, plus the losses due to the power Pd, power dissipation, multiplied with Rth, which is basically the heat sink in the intermediate zone of junction to ambient. So this RTHJA, junction to ambient, is basically calculated as the summation of three terms, which is junction to collector, collector to sink, and the sink to the ambient. The typical values of these RTH of junction to the case is basically in the 0.5 to 2 per degree centigrade per watt. So Tj maximum you will be getting 150 degree centigrade to 200 degree centigrade, and this will derate above 25 degree centigrade. The RTHSA, which is in the sink ambient, will be calculated using this formula. So this is the heat sink selection can be done by properly calculating the values of this register, which is the thermal equivalent circuit. So we have to do the proper thermal management and calculation depending upon the BJT power dissipation. Thermal protection and derating, where you have the protection methods you can accomplish using the temperature sensors, which is in the form of thermistors or RTDs. The thermal shutdown circuits also you have to incorporate, current limiting you need to do, and over temperature indicators has to be there. There are temperature effects, like when the beta will increase with temperature, so that is the positive temperature coefficient. The base to emitter voltage will decrease in the range of minus 2 millivolt per degree centigrade. The leakage current will double every 10 degrees centigrade. So in the reverse saturation current, which is the leakage current, you will be doubling every 10 degrees centigrade. There is the risk of thermal runaway in connecting when parallel with the devices. The derating guidelines, the power derating factor will be in the range from 2 to 5 millivolt per degree centigrade above the 25 degrees centigrade. So current derating will be there with temperature, and voltage derating will be there at high temperature. Frequency derating can also be there for switching applications. So the design margin, we have to use 50 to 70% of the maximum rating, then only you will have the proper design. So consider the worst case ambient temperature, what would be the temperature of the surrounding where you need to operate this device. You have to account for the aging effect as well, and include the safety factor for critical applications. Some of the major applications of power BJTs is in the switching And here in this application, you can use as DC to DC converter, which is in the form of buck boost or buck boost mode. You can have the inverter and the motor drive. There will be switching power supplies. UPS system also you can use it in the welding equipment and high frequency switching circuit. So these are the switching application. There are applications in the linear mode where you have audio power amplifier, linear regulators, servo amplifiers, test equipment, and the amplifiers in the class A and AB amplifiers. So these all things we have already discussed, where how the BJT are used for the class A, class AB amplifiers we have discussed in very detail. Some of the advantages in using these applications and some of the limitations also we need to discuss. Advantage of using the BJT is in the power mode is high current handling capability will be there. It is a good linear in active region, mature technology with proven reliability. It is being used for a long duration of the time. So cost effective for medium power application, and easy parallel operation can be done with ballast resistors. The limiting factors are basically it is very slow in terms of switching as compared to the MOSFETs, and it requires continuous base drive current. There is a storage time limit, switching frequency. So some of the advantages and limitations of Power BJTs are there, and due to these limitations we are moving to MOSFETs where we required high switching applications. Let us do one design example considering the buck converter switch to understand this Power BJTs. If you take the specification where the input voltage is 48 volt and the output voltage you require 12 volt, the load current will be 10 ampere. So switching frequency, let us take 20 kilohertz, and the target efficiency should be more than 85%. Now, the three important major step in this design will be first to select the BJT, where you need to do the proper design in terms of collector to emitter voltage, which should be greater than 1.5 times the input voltage. So input voltage is 48 volt. So 1.5 times will be 72 volt. Collector current maximum should be greater than 1.5 times the load current. So here the load current is 10 ampere. So you will be getting 15 ampere as the collector current maximum which you can pass. The power dissipation capability has to be there for the losses, and beta has to be greater than 20 in the minimum, and switching time should be less than the 1 microsecond for 20 kilohertz. So loss calculations, when you do the factor D, which is the ratio of V out by V in, is equal to 0.25. The conduction losses that you have is basically the losses, which is the product of collected to emitter saturation multiplied with the load current multiplied this factor D, which you have calculated here. This will be 3.75 watt. The base drive design, where you need to find the base current minimum, which is the ratio of the load current by base current minimum, which is 0.5 ampere. Base current on should be 3 times the base current minimum, so it will be 1.5 times 1.5 ampere, and the register of the base, which is coming from the Ohm's law, so the difference of the voltage from the base and base emitter by the base current in the on state. So you will get what value of the resistor you need to connect. Now we will be comparing all these power semiconductor devices. So this topic we are discussing on Power BJT. Next lecture we will discuss on MOSFET, then IGBT and thyristors. However, let us do the comparison here. So if you see the voltage rating, so Power BJTs are operated for 50 volt to 1500 volt, whereas MOSFET have less power rating, the voltage rating is 20 volt to 1000 volt, and IGBTs are higher as compared to the BJT, and you have the more than the thyristors. So thyristors are basically the silicon control rectifiers where you have higher voltage rating. Current rating, if you see, so it is up to 500 ampere BJTs, 200 ampere MOSFET, up to 3000 ampere you can go for IGBT, and 5000 ampere you can go for thyristors. Switching speed, if you compare, so switching speed is the most slow in BJT, and you will be getting very slow in thyristor, but thyristor have certain other important advantage. The fastest is the MOSFET. So if you require fast switching, you have to go with the MOSFET. Drive power requirement, if you talk about, then it is highest in BJTs and it is low in MOSFET, in medium category for IGBT and thyristors. The conduction losses, if you say, it is medium in BJT and you have very low losses in IGBT and thyristors. Low to high you will get in MOSFET. Switching loss, you will be getting high in BJT and low in MOSFET, medium in IGBT and low in thyristors. Control, if you talk about, then the BJTs are current control device, MOSFET is voltage control device, IGBT is also voltage control device, thyristor can be current control or voltage control. So this topic we have focused on power BJT. Next lecture we will see the power MOSFET and then go with the IGBT and thyristors. Selection guidelines generally is that if you want to operate for medium power, low frequency and you go for cost sensitive application, then prefer BJT. If you want high frequency, low medium power and efficiency critical, go for MOSFET. If you want high power, medium frequency motor drives application, go for IGBT. Very high power, low frequency and phase control, go for thyristors. So depending upon the application, you can choose the power semiconductor device among the four. Some of the technology trends and the future outlook, if you see, so the current trend, you are using the improved manufacturing process, better thermal packaging, enhanced switching, integration with drive circuits and smart power modules. So this is the current trend. Some of the niche applications you are having in the audio, which is superior linearity, RF powered amplifiers, in the military applications, cost sensitive consumer product and replacement or maintenance applications. There are certain challenges because competitions are there BJT with respect to MOSFET and IGBT. That is limited to switching frequency capability, base drive is complex and thermal management you required. Second, breakdown limitations is there in BJT which is not there in MOSFET devices. Future development you can use for silicon carbide and gallium nitride alternatives which are dominating, and specialized application focus are there for these devices. Improved manufacturing will be there for cost reduction, enhanced packaging technologies and smart power integration. So these are the future development in the category of semiconductor devices. Some of the key takeaways from today's discussion we have understood the power BJT, that is, it is a current control device. It required the base drive network. The storage time is dominating the switching behavior. Thermal management is very critical. Second, breakdown limit, operate the safe operating area. A lower current gain is compared to the small signal BJT. So small signal BJT, when you compare with the power BJT, the power BJT will be having the lower beta as compared to small signal BJT. Otherwise, the operation remains the same. We have discussed the design consideration, that is, base drive circuit is crucial, overdrive factor for reliable saturation, negative base current for fast turnoff, adequate heat sinking will be required for thermal management, and protection circuit will be there for safe operation. The applications we have discussed that it is best suited for medium power and low frequency. We have the cost effective for specific applications, linear applications benefit for good characteristic. Consider alternative when you require high frequency switching, parallel operation possible with proper design. The design process we have discussed that it define the specification and select the device, design the base drive circuit, calculate the losses and the thermal design, implement protection circuit and verify the safe operating area compliance. So in power BJT, which is similar to the small signal BJT, apart from that it is having the lower beta, and you have the certain difficulties in terms of base drive circuit, the thermal management, and you require adequate sinking protection circuit. So that you need to cover. In the next lecture, we will discuss these another semiconductor devices, which is basically the power MOSFET. So power MOSFET is the focus, which is high switching applications. So when you require fast switching, you have to go with the MOSFET as compared to the BJTs. So thank you for now. See you in the next lecture.